Hello there, and welcome to Sleepy Traveler. It's lovely to share this gentle quiet with you tonight. Wherever you are, allow the world's noise to dim and your thoughts to grow soft, like the moonlight outside your window. We are constantly searching for the fundamental recipe of the cosmos, the one elegant theory that explains both the immense gravity of galaxies and the tiny dance of quantum particles. Tonight, we're going to whisper about a beautiful and profound idea that everything we see and touch, from the planets to the atoms in your hand, might not be made of point-like particles at all, but of tiny, vibrating energy strands. This is the heart of string theory. We'll explore how these cosmic strings might create the entire symphony of reality, giving us a single, unified explanation for all the forces and matter in existence. If these peaceful scientific journeys bring ease to your mind and help you drift toward rest, a quiet like and a soft subscribe helps other sleepy souls find their way here too. For now, settle in. We'll begin our exploration of the universe's most elegant blueprint when you're ready. Physics carries a quiet worry, a little knot that has kept scientists restless for nearly a century. You can picture it like trying to understand a beautiful, tangled piece of music. You have two special ways of listening to it. One hears every delicate detail in the high notes, the soft trills, the tiny flickers, the quick, shimmering whispers. The other feels the deep bass, the slow, powerful rhythms, the way the sound seems to shake the room and move through space. Each method, on its own, is wonderful. When you listen with the first, the small things are crystal clear. When you listen with the second, the large, sweeping structure of the song makes perfect sense. But when you try to use them together, to hear the whole piece as one complete song, they do not agree. One tells you the music is doing something intricate and jittery, while the other insists it is smooth and heavy and calm. That is where modern physics finds itself. Two brilliant ways of hearing the universe that refuse to sing in harmony. The first way is called quantum mechanics. It describes the tiniest things we know: atoms, electrons, photons, and all the little quanta that make up reality. In this world, particles do not behave like tiny marbles. They move according to rules that feel more like a dream than like everyday life. A particle can spread out and behave as if it is in several places at once. It can slip through a barrier it should not be able to cross. As though the wall were made of mist, two particles can become entangled, so that touching one seems to echo mysteriously in the other, even across great distances. These strange rules are not just stories. They are tested and measured with exquisite care. Quantum mechanics sits behind the technology that quietly runs our lives. Computers, lasers, magnetic resonance imaging in hospitals, the electronics in your pocket. Some of its predictions agree with experiments to better than 1 part in 10 billion, as if the universe and the equations were breathing in perfect unison. The second great story is Einstein's general relativity. Instead of the tiny, it cares about the vast and the heavy. This is the language of gravity, of space and time woven together, of planets circling stars, of galaxies drifting, of black holes and the expanding universe. In this picture, space and time are not empty containers. They are like a flexible fabric. Massive objects press into this fabric, bending it, and that bending is what we feel as gravity. Things are not being pulled by invisible forces. They are simply following the natural curves in a warped landscape of space-time. General relativity has had its own quiet triumphs. It predicted black holes long before anyone was confident they could exist. It corrected the tiny, stubborn mismatch in Mercury's orbit that older theories could not explain. It suggested that the universe should be changing in size, not sitting still. And later observations of distant galaxies confirmed that space really is stretching. Like quantum mechanics, it is a masterpiece, elegant, powerful, and deeply successful. The trouble begins when we ask both stories to describe the same place at the same time. When physicists try to apply the rules of quantum mechanics to the curved space-time of general relativity, the mathematics does not simply become messy, it falls apart. The equations produce infinite, meaningless answers, like a radio turning from clear music into wild static. A simple picture is to imagine asking two very wise friends, "What time is it?" One calmly answers, "It is 3 o'clock." The other opens their mouth and begins reciting every line of Shakespeare backward. Both may be brilliant, but together they are not giving you a usable answer. That is the kind of confusion that appears when the quantum world and the relativistic world are forced into the same sentence. This clash matters most in the most extreme corners of reality. Deep inside a black hole, matter is squeezed into an incredibly tiny region, so quantum effects should matter a great deal. At the same time, the mass is so huge that gravity is overwhelmingly strong, so general relativity should also be in full control. At the very beginning of the universe, just after the Big Bang, everything was packed into an unimaginably small, hot state, again demanding both quantum and gravitational descriptions at once. In these places, our two great theories both want to speak, but together their voices turn into nonsense. Because of this, physicists have been searching for something more complete, a single framework that includes both the whisper of the quantum and the deep rumble of gravity. They sometimes call it a theory of everything. It is not a grand slogan so much as a gentle hope for unity, a way to describe all the forces of nature with one coherent language. In such a picture, the quiet fluttering of an electron inside an atom and the slow swirling of galaxies through space would be parts of the same story, like two melodies that belong in the same piece of music. String theory is one of the boldest candidates for this role. At first, it sounds like science fiction, an idea so radical and mathematically intricate that it feels far removed from ordinary experience. And yet, it may hold a key to why quantum rules and gravitational rules might actually fit together. The basic thought is surprisingly simple. Maybe the particles we call fundamental are not truly the smallest things. Perhaps electrons, quarks, photons, and all their cousins are not little dots with no size, but the visible notes played by something deeper. In string theory, that deeper something is a tiny vibrating string of energy. These strings are not like threads you can hold in your hand. They would be unimaginably small, far smaller than atoms, far smaller than anything our current instruments could ever see directly. Some estimates place their size around 10 to the power of minus 35 meters across, a scale so small it slips entirely out of intuition. What matters is not their size, but their motion. A string can vibrate in many different ways, just as the string of a violin can produce many notes. The shape of the vibration, the pattern of its trembling, is what makes the difference. In the musical instrument, a gentle pluck might give a low, warm tone, while a different touch brings out a high, bright note. The string itself is the same. It is the pattern that changes. In the world of string theory, each pattern of vibration corresponds to a different particle. One mode of vibration appears to us as an electron, with its particular mass and electric charge. Another mode of the very same kind of string shows up as a photon, carrying light. Yet, another vibration expresses itself as a quark with its own strange quantum properties. In this way, the many particles we see become different musical notes played by the same kind of underlying object. If this picture is right, the entire universe could be thought of as a quiet, unimaginable orchestra. Every bit of matter, every beam of light, every field and force would be part of a vast, silent symphony of tiny strings, each one humming its own note in the dark. The search for a theory of everything then becomes, in a sense, the search for the score of this cosmic music. Of course, this is not a finished song. String theory is extremely difficult to work with. The mathematics winds through extra dimensions and subtle structures that even experts grapple with. Many of its predictions live at energies far beyond what our experiments can reach, making direct tests very hard. Even its strongest supporters admit that parts of it are mysterious and incomplete. Yet the very existence of such a framework is quietly extraordinary. That human beings have been able to write down a consistent story in which quantum mechanics and gravity might both arise from vibrating strings suggests that reality might be more unified and graceful than it appears. It tempts us to imagine that the smallest ingredients of the universe are not little solid beads, but something closer to songs. For a long time, scientists were fairly satisfied with a different picture. Matter was made of atoms. Atoms had a nucleus of protons and neutrons, surrounded by electrons. Then, experiments revealed that protons and neutrons were not indivisible either. They were composed of quarks bound tightly together. Alongside these building blocks of matter, physicists discovered particles that carry forces: photons for light and electromagnetism, gluons for the strong nuclear force that holds quarks together, other particles for the weak force that allows certain particles to change their identity. Arranged carefully, these ingredients form what is known as the Standard Model, a kind of catalog of fundamental particles and their interactions. It works with remarkable accuracy, matching the results of particle accelerators and cosmic ray detectors. But there is an unease beneath its success. The Standard Model tells us which particles exist and how they behave, but not why this particular set of particles, with these particular masses and charges, should be the ones that reality chooses. It can write down the numbers, but cannot explain their origin. That is where the string idea begins to feel especially tempting. Instead of accepting dozens of different particles as separate, irreducible facts, string theory suggests that they might all be expressions of one underlying entity. Imagine replacing the whole zoo of particles with a single kind of object, the string. The diversity would come not from having many fundamentally different things, but from the rich variety of ways a single thing can vibrate. In that view, an electron would be one pattern of vibration, a photon another, a quark another. Still, the same simple ingredient, trembling in different modes, would give rise to the full cast of characters we see in nature. All the complexity and diversity of the particle world would emerge from the simple fact that strings can vibrate in many different ways. The strings of string theory are not quite like the strings of a guitar resting in someone's lap. They do not need to be nailed down at both ends or stretched across a wooden frame. In this picture, a string can close in on itself and become a tiny loop, a little ring of vibrating energy drifting freely through space. Or It can be an open strand with two loose ends, each tip able to quiver and sway in its own way. And while guitar strings vibrate in the three familiar directions of our everyday world, forward and back, side to side, up and down, these fundamental strings are said to vibrate in more directions than we can see. Their patterns fold and twist through extra dimensions hidden from ordinary sight. The equations that describe all this motion are intricate and demanding, tangled with ideas from the deepest corners of modern mathematics. Yet beneath all that complexity, the guiding thought stays wonderfully simple. Everything is music. In this view, every particle, every force, every invisible field is not a separate object, but a different song being played by vibrating strings. There is something quietly satisfying about that image. For a long time, people have spoken about the music of the spheres, the rhythm of the seasons, the harmony of natural cycles. We feel, almost instinctively, that there is a kind of order in the way things move and return. String theory whispers that this might be more than just poetic language. The universe itself might be a symphony, with every atom, every star, every gust of interstellar dust contributing its own faint voice to a cosmic composition. We cannot actually hear this music. The strings would be far too small, their vibrations far too rapid for our ears to notice. There is no sound in the air, no audible tune carried on the wind, and yet, in another sense, we are the music. Every atom in your body, every flicker of thought, every gentle beat of your heart would be part of that vast, invisible orchestration. You are not just listening from the outside. You are a phrase in the melody. Thinking in terms of vibrating strings also offers a way to understand why the basic numbers of nature take the values they do. Just as the pitch of a guitar string depends on its length, its tension, and its thickness, the properties of fundamental particles could depend on the exact way their strings are allowed to move. The mass of an electron, the strength of the electromagnetic interaction, even the speed at which light travels. These might not be random inputs, but the natural result of how strings vibrate within the underlying structure of space. It is a picture that is both richer and more unified than anything we have held before. Richer, because it calls for extra dimensions and subtle geometries that reach far beyond ordinary experience. Unified, because it suggests that all the variety we see, the many particles, the different forces, the patchwork of physical laws, might be different expressions of a single theme, the music of vibrating strings. Whether this musical vision of reality is truly how the universe works is still a deep, open question. But the mere fact that such a picture is mathematically possible, that the language of numbers allows for a cosmos in which everything is composed of vibration, is itself a quiet wonder. It hints that the world might have layers we rarely think about. Right now, as you listen, you may be wrapped in more dimensions than you can see or touch or even clearly imagine. In daily life, we move through three directions of space. You can go forward and backward, left and right, up and down. Those are the ways you can shift your body or your hand. When we add time as a fourth dimension, the way moments flow from earlier to later, we have what physicists call space-time, the stage on which all events unfold. String theory suggests that this familiar stage might not be the whole theater. According to the mathematics of vibrating strings, reality may include additional spatial dimensions beyond the three we know. Not just one extra direction, but perhaps 6 more tiny directions of space, which would make 9 spatial dimensions altogether, plus time. This raises a natural, almost childlike question. If extra dimensions are real, Why can we not walk into them? Why can we not step sideways into a fifth direction the way we step across a room? The answer in this framework is that the extra dimensions are compactified. They are not stretched wide like the big dimensions we roam through. Instead, they are curled up, folded in on themselves, wrapped into shapes so small that they are effectively invisible. A gentle way to picture this is to think of a garden hose lying on the ground. From far away, it looks like a simple line, thin and one-dimensional. You can see where it starts and where it ends, but from that distance, you cannot tell that the hose has a circular thickness. In truth, it has 3 dimensions: length, width, and depth, but 2 of them are curled into a tiny circle around the hose, too small to notice unless you come very close. String theory says something similar might be happening with space itself. What you experience as a single point in 3-dimensional space might actually have a tiny, intricate shape in higher dimensions. The extra directions are still there, but they are curled up so tightly, far smaller than atoms, that we have no direct way to sense them. Imagine you are an ant walking along that garden hose. To you, there are 2 genuine ways to move. You can walk along the length of the hose, covering a distance that would be obvious to someone watching from far away. Or you can walk around the circumference of the hose, looping in a small circle until you return to where you began. From the ant's point of view, both directions are equally real. From a distant human perspective, only the motion along the hose's length is easy to see. The circular motion around it disappears into the thickness of the line. We might be like those distant observers. We can move and watch motion in the 3 large dimensions of space, but the tiny circular journeys that might be possible in compactified dimensions are hidden from us. They are real in the mathematics, but they vanish from everyday sight. In string theory, these hidden dimensions are not just decorative flourishes. They play a crucial role in shaping the world we observe. The way the extra dimensions are curled, their size, their shape, their twists and folds affects the allowed vibrations of strings moving through them. And because different vibrations show up as different particles, the geometry of the hidden dimensions would determine which particles exist, what masses they have, and how they interact. It is like the difference between musical instruments. A violin and a guitar may both use strings under tension, but the shapes of their wooden bodies, the curves, the internal air cavities, all influence the tones they can produce. The same vibrating string will sing differently inside each instrument. In a similar way, the extra dimensions of string theory act like the body of a cosmic instrument, coloring and shaping the vibrations of strings into the particular spectrum of particles that fill our universe. This leads to a striking possibility. There may be many different ways to curl and fold the extra dimensions, many different shapes they can take. Each distinct arrangement would allow different patterns of string vibration, and that means different collections of particles, forces, and physical constants. Our universe, with its specific particles, its particular strengths of forces, its familiar speed of light, could be just one outcome among many, the result of one special way of folding the hidden dimensions. The mathematical shapes used to describe these folded spaces are fantastically complex. Some of them are known as Calabi-Yau manifolds, named for the mathematicians who studied them long before string theory needed them. They live naturally in 6 dimensions and have an intricate inner structure, tunnels, holes, loops, and twists that would make even the most elaborate 3-dimensional maze look simple. And yet, in this picture, such shapes might exist everywhere. Every point in the room around you, every speck of space between your fingers, could be more than just an empty dot. It could be a tiny, six-dimensional sculpture, folded so finely that no microscope could ever reveal it. Space would not be blank at all. It would be filled with delicate, hidden architecture woven into every location. There is something humbling and quietly beautiful about that thought. It suggests that reality is far richer than what our senses report. We move through the world, certain that we understand space, that what we see is what exists. But perhaps we are like creatures living on the surface of a vast ocean, noticing only the waves, never suspecting the great depth and strange life below. These hidden dimensions may also hint at answers to some long-standing puzzles. One of them is the weakness of gravity. Compared with other forces, gravity is astonishingly gentle. A small magnet on your fridge can lift a paperclip against the pull of an entire planet. In some versions of string theory, gravity may spread out into the extra dimensions, leaking into directions we cannot see, while the other forces remain confined to a three-dimensional brain, a kind of slice of the higher dimensional space on which our familiar physics lives. The more directions gravity can wander into, the weaker it appears within our slice. For now, the existence of extra dimensions remains a suggestion rather than a measured fact. We have no direct experimental evidence for them, no instrument that can probe such tiny curled spaces. They live, for the moment, in the equations of string theory and in the minds of those who study them. Whether they are truly part of the universe or only part of our mathematical imagination is still uncertain. But even as a possibility, they gently reshape how we think about existence. They remind us that the world may hold more than our senses can grasp, and that what feels obvious and complete might be only the surface of something deeper. It reminds us that the universe might be stranger and more wonderful than our everyday experience suggests. Right now, as you rest and let your thoughts wander, you can imagine yourself drifting not only through the familiar stretch of space and the gentle flow of time, but also through hidden directions, curled so small they slip between your thoughts. In that quiet picture, it is natural to wonder, what if gravity, electricity, and the forces that hold atoms together are not separate tricks of nature at all, but different instruments in one cosmic orchestra? In everyday life, they feel very different. Gravity is the steady pull that keeps your feet on the ground and makes apples fall from trees. It is always attractive, always drawing things together, reaching across any distance, though it grows weaker as things move apart. Electromagnetic forces are brighter and more changeable. They give us lightning and magnetism, run our devices, and hold atoms and molecules together through chemical bonds. Unlike gravity, they can attract or repel. They are far stronger, and they can be shielded and guided. Then there are two forces you do not feel directly, but that quietly protect the existence of matter. The strong nuclear force binds the centers of atoms, holding protons and neutrons together despite their urge to push apart. The weak nuclear force governs certain kinds of radioactive decay and plays a key role in the reactions that let the sun shine. These four forces, together, shape everything from galaxies to the chemistry of your cells. For much of the 20th century, physicists treated them as separate worlds. Gravity had its own equations, electromagnetism, its own elegant rules, the strong and weak forces, their own frameworks. It was as if four different orchestras were playing in four different halls, each with its own conductor and score. You could describe each concert beautifully, but there was no single piece of music that included them all. Gradually, patterns appeared. In the late 1960s and 1970s, physicists discovered that the electromagnetic force and the weak nuclear force are really two faces of one deeper interaction, the electro-weak force. At extremely high energies, like those just after the Big Bang, the two become indistinguishable. As the universe cooled, this single force split into the separate electromagnetic and weak forces we see today. It was like opening a wall between two halls and realizing both groups of musicians belong to one larger orchestra, following one underlying score. That success won major prizes and suggested that the apparent variety of forces might hide a deeper unity. Researchers then tried to fold the strong nuclear force into the same picture, building what they called grand unified theories. In the mathematics, these ideas were graceful. At even higher energies, three forces would merge into one. But when compared with certain observations, some predictions did not quite match reality. The vision was inspiring, but unfinished, and gravity still stood apart. It is extraordinarily weak compared with the other forces, yet it acts on anything with mass or energy. You can block electromagnetic forces with a metal shield, but you cannot hide from gravity. Einstein showed that gravity is really the curvature of space-time rather than a force in the same sense as the others, which makes it very hard to squeeze into their mathematical framework. Here, string theory offers a quietly radical possibility. In the string picture, all four fundamental forces arise from the same basic ingredient: vibrating strings. Different vibration patterns of the same kind of string give rise to the particles that carry each force. The photon, which mediates the electromagnetic force, would be a string vibrating in one specific way. The gluons of the strong force would be strings in another pattern. The W and Z bosons of the weak force would be yet other modes. Gravity fits into this story too. In string theory, the carrier of gravity, called the graviton, appears naturally when you look at strings that form closed loops instead of open strands. These closed loops vibrate in a special pattern that behaves like gravity. That simple topological difference that gravity is associated with closed loops, while the other forces can be linked to open strings, might explain why gravity feels so different. It would not be a separate kind of magic, just a different way for the same basic string to move. If this is right, the four fundamental forces are not truly four separate things. They are four melodies played by the same cosmic instrument. The universe becomes less like a collection of unrelated bands and more like one intricate symphony in which different sections carry different themes that weave together into the fabric of physical reality. String theory goes further still. The vibrations that show up as force-carrying particles and the vibrations that show up as matter particles could be different aspects of the same string dynamics. Electrons, quarks, photons, gluons, the particles that make up stuff, and the particles that mediate forces would all be expressions of one underlying phenomenon: strings vibrating within space-time. The line between what reality is made of and the rules that govern it begins to blur. One of the most quietly beautiful features of string theory is its internal consistency. Many other attempts to unify the forces feel like pressing mismatched puzzle pieces together, forcing separate mathematical systems to meet at awkward angles. String theory starts instead from a single idea: tiny strings moving in a higher dimensional space-time. When you ask that picture to be mathematically consistent, the unification of forces is not something extra you impose. It emerges naturally. In this view, at unimaginably high energies, like those in the first instance After the Big Bang, all the forces would truly merge into one. As the universe expanded and cooled, that unified interaction would have broken into separate pieces, much like white light passing through a prism splits into many colors. Gravity, electromagnetism, the strong force, and the weak force would be different shades of the same underlying light. There is a deep calm in that possibility. It suggests that beneath the tangle of phenomena we see, there may be a simple foundation. The electromagnetic force that powers your phone, the gravity that keeps planets circling their stars, the nuclear forces that fuel the warmth of starlight, each might be a variation on a single theme, different voices in one cosmic song. Proving that this song is truly the one the universe is playing is another matter. The energies where all the forces unify are far beyond the reach of our current experiments. We cannot build a machine that recreates those first moments of the cosmos. Instead, physicists look for indirect clues, subtle patterns in particle behavior, delicate imprints in the ancient light left over from the early universe, anything that might hint whether string theory's picture is close to the truth. Even without a final answer, this way of thinking changes the feel of ordinary experiences. Each time you flip a light switch, feel the tug of gravity, or trust that the atoms in your lungs will hold together, you might be touching different faces of one underlying reality, the music of vibrating strings, resonating through hidden dimensions. And when we look down to the smallest scales, that music starts to sound like jazz, full of improvisation and uncertainty. Quantum mechanics has always been the strange relative in the family of physical theories. In the familiar world, objects have definite positions and speeds. In the quantum world, particles exist in hazy clouds of possibility. They do not have precise positions or velocities until we measure them. They can be in several states at once, and sometimes slip through barriers that should completely block them. This is not just a problem with our tools or a gap in our knowledge. The uncertainty is woven into the rules of the microscopic world. It is as if the universe itself keeps its options open, choosing a definite outcome only when an interaction or observation forces a decision. Even empty space is not truly empty. In quantum mechanics, the vacuum boils gently with activity. Pairs of particles can briefly appear, borrow energy, and vanish again, as long as the borrowing is repaid quickly enough. At the tiniest scales, space-time foams and flickers. String theory invites us to replay this scene with strings instead of points. Rather than tiny dots dancing a jittery dance, we picture loops and segments of energy vibrating and weaving through space-time. This seemingly small change has powerful consequences. In ordinary quantum field theory, particles are treated as points with no size at all. Two such points can approach arbitrarily closely, even occupy the same place. When physicists compute how these point particles interact, the equations often produce infinite answers. Clever procedures can tame those infinities, but their presence hints that the picture is missing something. Strings, even though they are unimaginably small, are extended. They have length. Two strings can never truly collapse into one ideal mathematical point. When they meet, they join, split, and interact over a tiny but finite region. This gives the theory a natural minimum scale and smooths out some of the violent infinities that plague point particle theories. The interactions are spread out, more like strands crossing and braiding than needles colliding. You can think of the difference by imagining two sharp needles and two flexible guitar strings. Balance the needles tip to tip, and, in principle, they can meet at a single point, an unstable, almost singular contact. Tiny changes can make everything blow up. Lay two guitar strings across each other, and they touch along short segments. Their contact is softer, more stable. String interactions, in a mathematical sense, are like those overlapping strings rather than touching points. String theory also offers a fresh way to feel the ever-present uncertainty of the quantum world. In standard quantum mechanics, fuzziness arises because particles are described by wave-like states that only become definite when measured. In the string picture, that fuzziness may also reflect something more tangible, the fact that the underlying objects are always in motion, always vibrating. Imagine trying to photograph a vibrating guitar string. Even with the fastest camera, you would never capture the string completely at rest. It would always be in motion, blurred across multiple positions. Similarly, the properties of fundamental particles might be blurred because the underlying strings are never at rest, always vibrating between different configurations. In string theory, this constant trembling of tiny strings is more than just a pretty picture. The mathematics that describes those vibrations automatically includes the strange rules of quantum mechanics in a way that feels more graceful and self-consistent than many earlier attempts. One of the quiet surprises that falls out of the equations is something called supersymmetry, a deep symmetry that connects different kinds of particles to each other. In a supersymmetric world, every familiar particle would have a partner, a kind of shadow twin with slightly different properties. A particle of matter would have a partner that behaves more like a force particle, and vice versa. These partnerships are not just decorative, they help tame the wild quantum fluctuations that appear when you try to build a quantum theory of gravity. Instead of quantities blowing up uncontrollably, the contributions from partners can cancel and soften each other, like two singers holding a difficult harmony, steady. String theory also offers a new way of thinking about the quantum foam, the restless bubbling at the tiniest scales of space and time. In ordinary quantum field theory, we talk about particles popping into existence and vanishing again, borrowing a bit of energy from the vacuum and then paying it back. In the string picture, that restless bubbling becomes a dance of strings splitting and joining. A single loop might divide into two, the way a cell divides, or two loops might meet and merge into one. The drama is no longer about sharp points flicking in and out of nothingness, but about continuous strands reshaping themselves in an unending choreography. Even the old puzzle of measurement, the question of how fuzzy quantum possibilities become the single outcomes we actually observe, gets a new language here. Before an interaction, a string can vibrate in a superposition, a blend of different modes at once, like a chord with many notes sounding together. When strings interact with one another or with their environment, that interaction can act like a kind of musical conversation. The possible notes interfere, influence, and respond until the system settles into a definite pattern of vibration that corresponds to a particular particle state. In this view, quantum uncertainty is not a cold, abstract mystery we simply endure. It is a natural feature of a musical universe, a cosmos built from vibrations that can combine, split, and resolve into new harmonies. The universe improvises because it is literally made of something that behaves like music, and music, by its nature, flows and changes. It only becomes a single clear note after many possibilities have brushed against each other. All of this, for now, is theoretical. We do not yet have direct experimental evidence that strings exist, and the mathematical machinery needed to pull precise, testable predictions out of string theory is incredibly intricate. But as a framework, it gives us a way to picture the quantum world that feels less like chaos and more like composition. As you sink towards sleep, brainwaves slowing, thoughts softening at the edges, you can imagine yourself as part of this quantum dance. Every atom in your body, every chemical spark in your cells, every electrical whisper in your neurons would be part of a vast improvisation in which tiny strings vibrate through hidden dimensions, playing the quiet, complicated music that is you. Gravity, in this story, has long been the awkward guest. The other three forces, the electromagnetic, strong nuclear, and weak nuclear, fit snugly into the quantum world. They can all be described by quantum fields, by particles that carry their influence in tiny, discrete packets. Gravity, by contrast, always seemed to move to its own rhythm. Einstein showed us that gravity is not really a force pulling on objects from afar, but the curvature of space-time itself. Massive bodies like stars and planets warp the fabric around them, and objects follow the curves in that warped geometry. What we call falling is simply moving along the natural paths in a bent space-time landscape. This picture is breathtakingly successful. It explains falling apples, orbiting planets, bending starlight, and the overall expansion of the universe with elegant precision. The trouble comes when we try to let gravity share the stage with quantum mechanics at very small scales, where both should matter. Think of the interior of a black hole, where matter is pushed by gravity toward a density that Einstein's equations describe as infinite. Or think of the very first instant of the Big Bang, when all the matter and energy in the observable universe was crammed into a region smaller than a proton. In those extreme conditions, quantum effects cannot be ignored. The uncertainty principle tells us that at very small scales, space and time themselves should fluctuate wildly. Virtual particles should appear and disappear, bending space-time with their energy. But that bending of space-time feeds back into the quantum fluctuations, which then change the bending, which then change the fluctuations, and so on. The calculations spiral out of control, giving meaningless infinities. It is like trying to tune a guitar while someone shakes the tuning pegs. Every gentle adjustment is amplified and distorted, and the instrument never settles into a stable, harmonious note. For decades, physicists tried to cure this problem by applying the same techniques that had successfully unified quantum mechanics and electromagnetism. Gravity resisted. Its weakness at ordinary scales, its universality, touching anything with mass or energy, and its geometric nature all made it hard to squeeze into the familiar quantum mold. String theory offers what might be the first truly coherent approach to quantum gravity. The key is to stop treating gravity as something fundamentally separate. In the string picture, gravity emerges naturally from one particular way that strings can vibrate. The particle that would carry gravitational influence, the graviton, appears as the lowest energy vibration mode of a closed string, a loop with no ends. The particles that carry the other forces can be associated with open strings, tiny segments with two free ends. The graviton, by contrast, belongs to closed loops that can travel anywhere, including through the extra dimensions that string theory suggests. This difference in topology, in shape and connectedness, is subtle but profound. Closed strings can vibrate and twist in patterns that open strings cannot, spreading their influence across all dimensions. When you look at the simplest vibration of a closed string in the right setting, it behaves exactly like a graviton should, massless and tied to energy and momentum in just the way Einstein's curved space-time demands. String theory does more than give us a quantum description of individual gravitons. It hints at a deeper picture in which space-time itself is not fundamental, but emergent. The smooth, continuous space-time of general relativity could be like a photograph seen from far away, serene and unbroken. As you zoom in, the image is revealed to be made of pixels. At the smallest scales, string theory suggests that space-time might be woven from the interactions of strings, with a minimal, meaningful length scale set by the typical size of a string. Below that scale, the concept of distance stops making sense in the usual way. This pixelated view of space-time softens the infinities that appear when we treat particles as points moving in a smooth geometry. Strings cannot probe arbitrarily tiny distances because they themselves have extent. The violent processes that would produce infinite results in point particle theories are gently cut off at the string scale. The mathematics, while still hard, becomes better behaved. The extra dimensions of string theory also offer a graceful explanation for why gravity feels so weak compared with the other forces. If our familiar world is like a three-dimensional sheet, a brain embedded in a higher dimensional space, most of the forces we know may be confined to that sheet. Their associated open strings have endpoints stuck to the brain, unable to wander into the hidden dimensions. Gravity, carried by closed strings, is different. Closed loops can slip off the brain and spread their influence into all the dimensions that exist. That spreading dilutes the strength of gravity we feel on our three-dimensional slice, making it seem much weaker than it truly is. Perhaps most intriguingly, string theory suggests that the relationship between gravity and quantum mechanics might not be a fight to be resolved, but a partnership. The same quantum uncertainties that seem to threaten the smoothness of space-time in Einstein's picture may be what gives rise to space-time in the first place. The vibrations of fundamental strings would create not just particles and forces, but the very stage on which those particles and forces move. In that sense, gravity no longer has to stand in the corner, separate from everyone else. It becomes one voice in the same cosmic symphony, played by closed strings, vibrating through a universe that is deeper and more musical than our day-to-day senses reveal. The mathematics of this vision is still being explored, and experiments have not yet confirmed it. But, for the first time, there is a framework in which quantum mechanics and relativity might both be understood as expressions of something more basic: the music of vibrating strings resonating through the fabric of reality. Within this world of strings, shape matters as much as mass or energy. Some strings have free ends that can wiggle and move. Others close in on themselves, forming tiny loops like cosmic rubber bands with no beginning and no end. This is where topology, the study of how things are connected, comes to the foreground. The difference between a string with two loose ends and one that forms a closed loop may sound small, but it has deep consequences for the particles and forces that emerge. Open strings are easier to picture. Imagine a segment of thread so tiny that an atom would look enormous beside it. Both ends of this thread can vibrate, sending ripples along the string. Those ripples can form standing waves, patterns that repeat along the length, and each possible pattern corresponds to a different kind of particle. The defining feature of open strings is that their endpoints are free to move, but not completely free. In many versions of string theory, the endpoints of open strings are tied to higher dimensional surfaces called D-branes, which you can think of as vast, thin membranes stretched through space. Some of these branes may extend through the extra dimensions that string theory requires. Our familiar three-dimensional world might, in fact, be one such brane, a three-dimensional surface floating in a higher dimensional space. The endpoints of open strings would be stuck to this brane like tiny flies on a sheet of invisible paper. They could slide and dance along the surface, giving rise to particles that move through the three directions we know, but they could not lift off and roam freely into the higher dimensional bulk. This gentle confinement offers a way to understand why we see particles moving in three spatial dimensions, but do not notice motion through any additional directions that might be there. The endpoints remain glued to our brain, able to slide across it, but unable to leave it entirely. This confinement might explain why we observe particles moving through three-dimensional space, but not through the additional dimensions that string theory predicts. The vibrations of open strings are thought to give rise to many of the particles we know so well: electrons, quarks, photons. The familiar building blocks of atoms and light could all be different standing wave patterns along tiny open strings. Each pattern of vibration, each arrangement of peaks and troughs along the string's length would correspond to a particle with its own mass, electric charge, and behavior. Change the pattern, and you change the particle. But open strings come with a quiet restriction. Their endpoints are tied to D-branes, those higher dimensional surfaces that may include our three-dimensional world. Because the ends cannot wander freely into the higher dimensional space, the forces they generate are also confined. Electromagnetic forces, the strong and weak nuclear forces. All the interactions between matter particles would be trapped on the same brane we inhabit. They would play their music along the surface of our world but not spill into the extra dimensions that might be wrapped up around us. Closed strings are different. With no endpoints to pin them down, they are free to roam through all the dimensions of space, including the hidden ones. You can imagine them as tiny cosmic hoops, hula rings of energy that can move and vibrate in ways open strings simply cannot. In string theory, the simplest, lowest energy vibration of a closed string looks like what physicists call a graviton, the hypothetical particle that carries the influence of gravity. Because closed strings can slip off the brane and travel through the entire higher dimensional space, gravitons would not be confined to our three-dimensional world. They would spread out into all available dimensions, sharing their energy across a much larger volume than the other forces. This spreading could be why gravity feels so faint compared with electromagnetism or the nuclear forces. It is like shouting in a narrow hallway versus in a vast cathedral. In the hallway, your voice is concentrated and loud. In the cathedral, the same sound washes out in all directions, becoming softer and more diffuse. Gravity might be the voice in the cathedral, whispering through dimensions we cannot see. Closed strings can also vibrate in more elaborate ways than open strings. They can twist, shrink, swell, and ripple through complex patterns that have no direct counterpart in the vibrations of open strings. Some of these modes might correspond to particles or fields we have never observed, exotic forms of matter and energy that interact so weakly with ordinary particles that they have remained hidden in the background of our experiments. The distinction between open and closed strings has deep implications for the very shape of space-time. Open strings tied to D brains mostly feel the geometry of those brains the way our three-dimensional world is curved or stretched. Closed strings, by contrast, respond to the geometry of all of space, including the extra curled-up dimensions. Their vibrations can help determine the size and shape of those hidden directions, adjusting the geometry as they move, like musicians reshaping a room with the sound they produce. From this viewpoint, the familiar three-dimensional space you move through each day might not be the most fundamental layer. Our brain could be like the surface of a lake, a thin, seemingly solid boundary that arises from the deeper behavior of the water and air around it. In the same way, our world might emerge from the interplay of strings in a higher dimensional space, a surface reality resting on a more intricate, hidden structure. Some versions of string theory even suggest that open and closed strings can transform into one another. An open string sliding along a brain might curl up and join its ends, lifting off as a closed loop into the higher dimensional bulk. A closed string drifting through the bulk might strike a brain and split into two open strings attached to it. To an observer living on the brain, such events would look like matter particles disappearing into nowhere or new particles appearing from empty space, when in truth, they are part of a larger exchange between the brain and the surrounding space. The mathematics describing these processes is challenging and intricate, full of advanced geometry and topology, but the image it paints is softly simple, reality emerging from two intertwined kinds of cosmic music. There are the confined melodies of open strings, playing along the surfaces we call worlds, and the free-flowing harmonies of closed strings, resonating through all dimensions. Whether this picture is literally true is still unknown. We have no direct evidence yet for D-brains, extra dimensions, or strings themselves. For now, they live in our equations and in the minds of those who study them. Still, the internal consistency and elegance of the framework continue to draw physicists and mathematicians toward it, like listeners drawn to a piece of music whose structure feels just right even before all its themes are understood. It hints that the deepest layer of reality might be far more musical and interconnected than our senses alone would ever suggest. As you drift towards sleep, your awareness settling like ripples fading on a pond, you can imagine yourself as part of this ensemble. Your thoughts and dreams could be seen as the gentle play of open strings confined to our three-dimensional brain, while gravity and the shape of space-time itself arise from the deeper, quieter harmonies of closed strings moving through hidden dimensions beyond perception. And then a further, stranger possibility opens. What if our entire universe is just one bubble in an endless bath, floating alongside countless others we will never touch? String theory does not stop at the idea that everything inside our universe might be made of vibrating strings. It also leans towards something more astonishing, that our universe itself might be only one of many, each with its own laws of physics and its own story. This idea grows naturally out of the mathematics. In string theory, the properties of particles and forces depend heavily on how the extra dimensions are curled up, on the precise ways those hidden directions are folded and knotted. But there is not just a single way to wrap 6 extra dimensions into a tiny space. There are many ways, perhaps unimaginably many. Each distinct folding produces a different pattern of allowed string vibrations, and therefore a different possible universe. In one such universe, electrons might be heavier or lighter. In another, gravity might be stronger or weaker. In others still, there might be entirely unfamiliar particles and interactions, nothing like those we know. The range of possibilities is so vast that physicists sometimes call it the landscape, a broad terrain of potential realities stretching beyond what we can fully map. You can picture it as a gigantic garden. Each flower is a possible universe. Some blossoms grow close together and look similar. Universes where only a small detail, like the mass of one particle, is changed. Others are wildly different, with entirely different arrangements of forces, different numbers of dimensions, different ways of building matter and energy. Our own universe would be just one flower in this infinite garden, precious to us because we live in it, but perhaps not singled out by any special rule of nature. We might exist here not because this universe is the correct one, but because it is one of the rare places where stars can form, planets can persist, chemistry can flourish, and life can arise. In many other regions of the landscape, the physical constants might be so different that atoms never stabilize, or stars collapse too quickly, or space itself is too unstable to host complexity. In such universes, there would be no observers to wonder about anything at all. This way of thinking is related to something called the anthropic principle. It says that we observe the physical constants we do not, necessarily because those values are the only possible ones, but because they are among the values that allow observers to exist and ask questions. It is a bit like looking at a wedding photograph, where everyone is smiling and concluding that humans must always be happy. In reality, the picture was taken at a special moment, chosen and arranged in a particular way. Our universe may be a kind of selected snapshot from a much larger collection in which most frames contain no observers. The multiverse implied by the string landscape goes beyond simply adjusting known numbers. In some corners of this space of possibilities, the basic structure of reality might be different. There could be universes with more or fewer spatial dimensions, with time behaving strangely, or with building blocks that are not particles in any sense we recognize. In those places, the very language we use for physics might not apply. Some physicists feel uneasy with such a vast spread of possibilities. If almost anything can happen somewhere in the multiverse, it becomes harder to extract sharp predictions about our own universe. The theory risks becoming more like a general framework that can accommodate many outcomes than a precise tool that singles out one. Others find the idea freeing. It offers a gentle explanation for the apparent fine-tuning of our universe without invoking special design. In an enormous landscape, it is not surprising that some regions naturally support complexity in life, while most do not. We find ourselves in one of the rare hospitable patches simply because nowhere else could we exist. The multiverse idea can also be woven into our understanding of quantum uncertainty. When quantum theory tells us that a particle is in a superposition of many possible states, one interpretation is that these possibilities are realized in different branches of a larger reality. What looks to us like a single outcome selected from many might, in a multiverse picture, be one path among countless others, each taken in a different universe. Our sense of randomness becomes a reflection of our limited view of a larger structure in which all possibilities unfold. The most profound consequence of this thinking is what it says about existence itself. If every mathematically consistent possibility is realized somewhere in the landscape, then reality is not a single line of events, but more like an infinite library. Every story that can be written exists on some shelf. Every choice made and not made. Every path followed and every path left unexplored. Every alternate history quietly playing out in another volume. These universes would not be places we could travel to or send messages between. They would be separated by gaps so vast that no light signal, no influence of any kind could ever bridge them. Each universe bubble would be an isolated island of reality, drifting in a sea of possibilities, forever out of contact with its neighbors. There is something both humbling and quietly comforting in that picture. Humbling because it hints that everything we can see, the billions of galaxies, the uncountable stars, might be just one small bubble in a vast foam of realities. Comforting because it suggests that every possibility for beauty, structure, and meaning may be realized somewhere in the full sweep of existence, even if we only ever touch one small corner of it. String theory does not firmly declare that this multiverse is real. The mathematics allows such a landscape, but turning possible into proven is one of the deepest challenges in modern physics. By definition, we are confined to observing our own universe. Any hint of other universes would have to come in directly, perhaps as subtle fingerprints in the cosmic microwave background, or as tiny anomalies in the way space expands or light travels. Still, the fact that our most ambitious theories naturally lead us to imagine infinite gardens of reality suggests that the cosmos, perhaps the multiverse, is stranger and more generous than our ancestors ever dared to dream. As you drift towards sleep and your mind begins to wander through its own inner landscapes, you can imagine yourself floating through that great garden of possibilities. Each dream might be like a soft echo of what reality could feel like in some distant branch of the infinite tree of existence. Inside every point in space, smaller than anything you can picture, there may be 6 extra dimensions curled up and hidden. We touched on this before, but it is worth taking a gentler, closer look. If string theory is right, then every point around you is not really a point at all. It is a tiny, intricate 6-dimensional shape, folded and twisted in ways so delicate that even the finest origami would seem crude by comparison. These shapes have names that sound as if they belong in a fantasy novel. Calabi-Yau manifolds, after Eugenio Calabi and Xingtong Yao, who explored their properties long before anyone guessed they might describe the hidden architecture of the universe. Yet, as exotic as they sound, these geometries could be among the most fundamental ingredients of reality, helping decide why the universe behaves exactly as it does. To sense how extra dimensions can hide, imagine looking at a basketball from across a gym. From that distance, it appears as a smooth, simple sphere. Walk closer, and you see the textured bumps that give it grip. Zoom in further still, and you would find a complex network of molecules. In the rubber, the ball was never truly smooth. The detail was simply too fine to notice. In string theory, something similar might be true of space itself. What looks like a simple 3-dimensional point may, if you could zoom in far enough in the right way, reveal a rich internal structure, extending into extra dimensions instead of just finer detail in the familiar ones. Every location in our 3-dimensional space is like that basketball, seemingly simple from afar, secretly elaborate within. Why 6 extra dimensions and not some other number? The answer is hidden in the demand that the equations of string theory remain consistent and free of certain contradictions. When you follow that requirement, you find that space needs a total of 9 dimensions, plus time. We directly experience 3 of those spatial dimensions. The remaining 6 must somehow be curled up and hidden. They cannot be folded arbitrarily. To preserve the delicate symmetries of the theory, these 6 dimensions must be wrapped into very specific shapes. Those shapes, the Calabi-Yau manifolds, solve intricate geometric equations. They live naturally in 6 dimensions, with tunnels, loops, and connections twisting through directions we cannot visualize. You can imagine starting from a simple surface, adding handles and tunnels, then adding more and more connections in ways that would tangle any ordinary picture. All of that compressed into a region unimaginably smaller than an atom. These are not just abstract toys for mathematicians. In string theory, the exact shape of the Calabi-Yau manifold at each point in space influences how strings can vibrate there. Just as the tone of a violin depends on the shape and wood of its body, the sound of the strings, the spectrum of particles and forces, depends on the hidden geometry they move through. Different tunnels and holes in the manifold correspond to different possible vibration patterns, and those patterns show up to us as particles with particular masses and charges. The 6-dimensional shape acts like a cosmic instrument, and the strings are the musicians. The physics we observe is the music they create together. This picture has surprising consequences. It suggests that what we call the laws of physics might, in part, reflect the specific geometry folded up in the region of space we inhabit. If the Calabi-Yau shape were slightly different elsewhere, some of the fundamental constants might shift as well. The strength of forces, the masses of particles, even the number of stable particles could, in principle, depend on the local details of the hidden dimensions. What feels like universal law might be, at least in part, a local dialect spoken by our patch of the higher dimensional landscape. There is also the tantalizing thought that these extra dimensions might not be perfectly frozen. Over immense spans of cosmic time, they could, in some models, slowly change shape as the universe evolves. That gentle evolution might cause physical constants to drift ever so slightly, leaving faint traces in the light of distant galaxies or in the afterglow of the Big Bang. Other variations of string theory allow for extra dimensions that are larger than we once assumed, perhaps large enough that, at extremely high energies, particles in a collider could slip into them. To us, that would look like missing energy. The particles seem to vanish, when in fact, they have taken a small detour into directions we cannot see. The space of all possible Calabi-Yau shapes is enormous. Even with modern computers and clever mathematics, physicists have explored only a tiny subset of the possible 6-dimensional geometries. Each one would give rise to a different low-energy physics, a different way a universe could work. Our particular shape, the one that yields the particles and forces we observe, is just one point in this vast landscape. As you rest, you can imagine these hidden dimensions tucked inside every atom of your body, like tiny 6-dimensional gardens, more intricate than any carved cathedral, all nested inside spaces smaller than anything you can consciously picture. Every breath, every flicker of thought would be tied to strings vibrating through these invisible shapes, composing the reality you experience from music played in dimensions beyond perception. And the orchestra might be larger than we see. One of the most delicate and mysterious ideas linked with string theory is supersymmetry, the suggestion that every particle you know may have a secret companion, a shadow partner moving just beyond the edge of our experiments. To feel what supersymmetry is reaching for, it helps to remember that nature divides particles into 2 broad families. There are those, like electrons and quarks, that make up matter and have half-integer spin. These are called fermions, named after Enrico Fermi. They are solitary in a very specific way. No two identical fermions can occupy the same quantum state. This rule, the Pauli exclusion principle, is what keeps electrons in atoms from all collapsing into the lowest energy level, and is part of why matter has structure and solidity. Then there are particles like photons and the hypothetical graviton that carry forces and have integer spin. These are called bosons, after Satyendra Nath Bose. Bosons are sociable. They are happy to crowd into the same state, piling on top of each other. This tendency is what makes phenomena like laser light possible, where enormous numbers of photons move in lockstep, sharing the same quantum state and marching together like a perfectly synchronized parade. Supersymmetry proposes a hidden balance between these two families. For every fermion in nature, there would be a corresponding boson, and for every boson, a fermion-like twin. Every matter particle would have a force-carrying partner, and every force carrier a matter-like shadow. The electron would be paired with a partner called the selectron. The photon would have a partner called the photino. Quarks would have squark partners. Neutrinos would have sneutrino partners, and so on, each ordinary particle matched with a supersymmetric companion. These pairs would be like quantum dance partners, linked by a deep symmetry woven into the fabric of the laws themselves, moving in step even when one of them remains hidden from our direct view. It is a lovely idea, this hidden pairing of particles and their supersymmetric twins. But then, a quiet question arrives. If every particle has a partner, where are they? We have never seen a selectron in a detector, never caught a glimpse of a photino streaking through our instruments, nor any of the other shadow companions that the theory seems to promise. According to supersymmetric theories, the answer is not that these partners do not exist, but that the symmetry linking them is broken in our present universe. The symmetry is still there in the deep mathematics, like a perfect face behind a distorted funhouse mirror. What you see in the mirror does not match you exactly, but the underlying symmetry between you and your reflection has not vanished. It is simply warped by the shape of the glass. In the early universe, when temperatures and energies were unimaginably high, supersymmetry may have been unbroken. Particles and their superpartners could have had the same masses and very similar properties, moving almost as equals in that hot, dense sea. But as the universe expanded and cooled, something in the cosmic environment shifted. The symmetry broke. The superpartners became much heavier than their ordinary twins, so heavy that they would have been unstable, decaying quickly into lighter, familiar particles. This breaking of supersymmetry is not just an inconvenience. It may be essential to the way our universe works. If supersymmetry were still perfectly intact at low energies, every electron would march alongside an equal mass selectron, every photon with a photino of the same weight, every quark with a squark twin that never decays. The resulting world might be so different that the delicate structure of atoms and chemistry could not form. The quiet arrangements that allow stars, planets, and living cells might never arise. Even though supersymmetry appears to be hidden or broken in our cool, low-energy universe, it remains central in many versions of string theory. In fact, string theory seems to need supersymmetry to remain mathematically healthy. Without it, the equations tend to produce problematic states, often called tachyonic modes, which behave like particles with negative mass squared, signaling instabilities that would tear the theory apart and allow violations of causality. Supersymmetry smooths these rough edges. It also helps with the technical challenge of uniting quantum mechanics and gravity. In quantum field theories without supersymmetry, contributions from different virtual particles and loops can grow without bound, leading to infinite answers that must be patched by delicate cancellations. With supersymmetry, many of those troublesome contributions from fermion loops and boson loops cancel each other more naturally. The result is a more finite, better behaved set of quantum corrections, like a turbulent piece of music suddenly resolving into a quiet, balanced chord. There is something quietly beautiful about this idea. Supersymmetry suggests that the universe is built with an underlying balance, a kind of cosmic yin and yang, in which every type of particle is paired with a complementary opposite. Matter is balanced by force, half-integer spins balanced by integer spins, and wild quantum fluctuations softened by the presence of unseen partners. And yet, for all its elegance, supersymmetry remains unconfirmed. Particle colliders have been listening for the footfalls of superpartners for decades, but no unmistakable signal has yet arrived. This does not prove that supersymmetry is wrong, but it does push the likely mass of the superpartners higher and higher, beyond the reach of current machines. If they exist, they may be heavy enough that we can only feel their influence indirectly. Like distant thunder, we hear, but never see. Some physicists remain hopeful that with more powerful accelerators or more sensitive experiments, hints of supersymmetric particles will finally appear. Others worry that if supersymmetry is realized in nature, it may be broken so severely that the partners are forever beyond experimental reach. They would be part of the cosmic blueprint, but not something we can ever directly produce or capture. There is also a gentle, intriguing possibility. The mysterious dark matter that makes up most of the mass in the universe might be made of supersymmetric particles. If the lightest superpartner is stable, does not decay, and interacts only very weakly with ordinary matter, it would be invisible to telescopes, but would still tug on galaxies with its gravity. It would be a perfect dark matter candidate, silently shaping cosmic structures while staying hidden from view. The mathematics of supersymmetry itself has a kind of crystalline beauty. It links the geometry of space and time with the behavior of quantum fields in ways that seem almost too neat to be coincidence. Whether that beauty reflects a deep truth about nature or is simply a mirror of our own aesthetic preferences is still unknown. For now, supersymmetry sits in a liminal space, compelling, consistent with string theory, but not yet confirmed by experiment. As you relax into the quiet of approaching sleep, you can picture a hidden mirror world of supersymmetric particles, shadow twins of every atom in your body, every photon of light that has ever brushed your eyes, every quantum field that hums through space. They would be present in the equations, yet absent from direct experience, real in a deep mathematical sense, and yet unreachable, like reflections on the surface of a still lake you can see but never grasp. In that picture, you are never entirely alone. Some delicate symmetry is always there in the background, a silent partner in the dance of existence. Then comes an idea from string theory that may be even stranger than tiny strings or hidden dimensions. It is the suggestion that everything you experience might be a kind of projection. Imagine holding a hologram in your hand, a flat piece of plastic that somehow contains a shimmering three-dimensional image. As you move your head, the image shifts, revealing different angles of a figure that seems to stand in space. Yet all of this depth and motion is encoded on a thin, two-dimensional surface. Now take that image and expand it to a cosmic scale. What if the three-dimensional world you move through, with its sense of depth and volume, with room for stars and galaxies, and the chair beneath you, is itself a kind of hologram? What if all the information needed to describe everything that happens in 3 dimensions is actually stored on a distant 2-dimensional boundary? This is not just a poetic thought experiment. It is a serious proposal known as the holographic principle, one of the most revolutionary ideas to emerge from studies connected to string theory. The story begins with black holes, those regions of space-time where gravity is so intense that nothing, not even light, can climb out once it falls in. In the 1970s, physicist Jacob Bekenstein made a surprising discovery. The entropy of a black hole, the measure of how much information it can contain, is not proportional to its volume, but to the area of its surface, its event horizon. That is like discovering that the amount of information in a library depends not on how many books it has, but on the size of its walls. Soon after, Stephen Hawking showed that black holes are not perfectly black. They emit a faint radiation due to quantum effects near the horizon. Over very long times, they can slowly evaporate. This created a puzzle. If objects carrying information fall into a black hole and the black hole then evaporates into featureless radiation, the detailed information about what fell in seems to vanish forever. But quantum mechanics insists that information cannot be destroyed. This tension became known as the black hole information paradox. String theory and the ideas connected to it offered a different way to see what is going on. The holographic principle suggests that all the information that appears to be inside the 3-dimensional volume of a black hole can be encoded on its 2-dimensional horizon. The interior, in this view, is more like a holographic projection of data written on the surface. The information is never truly lost. It is stored in a scrambled form on the boundary. Once you accept that such a holographic description can work for black holes, a further, bold step presents itself. Perhaps the entire universe can be described holographically. Maybe everything we perceive as happening in a 3-dimensional volume, every star, every cloud, every neuron firing in your brain is mirrored by information living on a distant 2-dimensional boundary, perhaps at the edge of the observable universe or beyond. In certain simplified models of space-time, physicists have been able to work out this correspondence in astonishing detail. They can write down one theory that lives in a 3-dimensional space with gravity, and another theory that lives on a 2-dimensional boundary without gravity, and show that they are exactly equivalent in how they encode information. Every field, every particle, every interaction in the bulk 3-dimensional space matches something on the flat boundary. In that framework, the 2-dimensional description is often considered more fundamental. The 3-dimensional space, with its sense of depth, emerges as a convenient way of organizing the boundary information. Just as the moving shapes in a film are emergent patterns built from pixels on a screen, you can think of it like watching a movie in a dark room. The story unfolds in what appears to be a 3-dimensional world. Characters walk through rooms, drive cars down streets, gaze up at the sky. Yet, all of this is created by a flat screen at the front of the room, where tiny patches of light change rapidly. The 3-dimensional world of the film feels real while you are absorbed in it. But the more fundamental reality is the 2-dimensional pattern of light. The holographic principle invites us to consider that our universe might be like that film, not in the sense of being fake or unimportant, but in the sense that the three-dimensional stage we experience may not be the most basic layer. The underlying screen would be a distant surface where the true information is stored, while the space we move through is a derived, emergent picture. This idea even sheds light on quantum entanglement, that spooky connection between particles that can remain linked across vast distances. In the holographic view, particles that seem entangled in the three-dimensional interior correspond to neighboring or connected regions on the two-dimensional boundary. The strange correlations we observe might reflect ordinary geometric connections in the holographic encoding. What looks non-local in the bulk can be simple and local on the boundary. There is a quiet unease and a quiet beauty in all of this. It is unsettling to be told that the space you feel so sure of, the depth in which you reach out your hand, might be more like an image than a basic fact. Yet it is beautiful to discover such a deep unity, that the same information can be described perfectly in two very different languages, one living on a surface, one filling a volume. The techniques born from this holographic thinking have already found uses beyond pure cosmology. They have given physicists new tools to study complicated quantum materials, where particles interact so strongly that traditional methods falter. By mapping a hard three-dimensional problem into an easier two-dimensional one, the holographic dictionary offers fresh ways to understand superconductors, quantum fluids, and other exotic systems. Still, perhaps the most profound echo of the holographic principle is not in these practical applications, but in what it whispers about the nature of information and reality. If everything you experience can, at the deepest level, be described as information written on some faraway surface, then information begins to look more fundamental than space, time, matter, or energy. Reality becomes, in a quiet but profound sense, informational rather than material. This way of seeing the world brushes against some of the oldest questions in physics and philosophy. What is consciousness? How does a private, inner experience arise from what we usually treat as objective, physical processes? If reality is fundamentally information, then perhaps consciousness is a particular way in which information flows, loops back, and becomes aware of itself. As you slip towards sleep, your hold on ordinary, three-dimensional experience loosens. You can imagine yourself as both the pattern and the picture, both the data encoded on some distant cosmic boundary and the rich, three-dimensional life that emerges from that code. In dreams, space and time already soften and bend. Distances shrink, moments stretch, scenes dissolve into one another. In a gentle way, sleep might be a tiny hint of what it would mean to step outside the holographic projection and glimpse reality from the side of the encoding screen. But not everyone is persuaded that the universe is woven from music and holograms, and their doubts are thoughtful. String theory is undeniably beautiful. The equations are elegant. The vision of unity is compelling, and the hope it offers for resolving deep puzzles about gravity and quantum mechanics is real. Yet beauty alone is not enough to make a theory true. Some of the sharpest minds in physics have raised serious questions about whether string theory deserves its place as the leading candidate for a theory of everything. One of the most basic concerns is about prediction. In science, a theory does not earn its keep just by being internally consistent or aesthetically pleasing. It must make clear, testable predictions that can be checked against observation. Einstein's relativity, for instance, predicted that light would curve around massive objects, that clocks would slow in strong gravitational fields, and that ripples of gravity would travel through space-time. Over the years, these predictions were seen in starlight bending during eclipses, in precise time measurements near Earth, and in the detection of gravitational waves. Each confirmation strengthened the case that relativity describes something true about the world. String theory, despite many decades of intense work, has struggled to produce predictions of that kind. The distinctive effects of tiny strings are expected to show up only at energies that existed in the first instance after the Big Bang, far beyond what our experiments can reach. The extra dimensions, if they are small, are curled so tightly that they lie far below the resolution of any conceivable microscope. The supersymmetric partner particles that string theory seems to favor have not appeared in our particle collider data. Critics say that without concrete, falsifiable predictions, string theory looks less like a scientific theory in the traditional sense and more like a broad mathematical framework within which many different physical scenarios can be imagined. A second related worry is known as the landscape problem. We talked about how different ways of folding the extra dimensions give rise to different possible sets of particles and forces. The trouble is that the number of possible foldings is not just large, it is astronomically huge, perhaps something like 10 to the power of 500. Each distinct geometry would correspond to a different possible universe with its own physics. With so many options, it becomes very hard to extract sharp predictions. If almost any set of physical constants can be realized somewhere in this landscape, then string theory can be made to fit almost any observation by choosing the right compactification. It is like trying to predict the outcome of a coin toss by saying, every possible sequence of heads and tails occurs somewhere. True, in a broad multiverse sense, perhaps, but not very helpful for predicting what you will see when you actually flip a coin. This connects to what physicists call naturalness. A natural theory is one in which the values of physical constants emerge without delicate fine-tuning, as straightforward consequences of deeper principles. In the string landscape, getting a universe that looks like ours seems to require singling out a very special corner from an almost limitless range of possibilities. It is like picking one grain of sand from all the beaches on Earth, and then asking why this particular grain is under your foot. Some string theorists lean into this picture and invoke the anthropic principle. We see the constants we do because they are among the rare combinations that allow stars, chemistry, and observers. In universes where the numbers come out differently, no one is there to ask questions. Critics find this unsatisfying. They worry that it shifts the focus away from understanding why our universe is the way it is, and toward simply accepting that it is one of many. There are also technical criticisms. Much of string theory is studied using approximation methods that work best in certain limits, when some coupling is weak or some curvature is small. Famous successes, such as reproducing the entropy of specific black holes, often rely on these controlled regimes. It is not always clear how far those results extend once you move away from the limits where the approximations are valid. The theory also rests on assumptions that, from a distance, can feel arbitrary. Why should the fundamental objects be one-dimensional strings instead of two-dimensional sheets or point-like particles? Why exactly this number of space-time dimensions and not another? Within the mathematics of string theory, these choices are justified by consistency. If you try to change them, anomalies and contradictions appear. But that raises a subtle question. Is mathematical consistency alone a strong enough reason to believe that a particular structure describes the physical world? Some critics go further and point to sociological issues. They note that string theory became so dominant in parts of theoretical physics that alternative ideas about quantum gravity struggled to gain attention and support. Young researchers, hoping for jobs and careers, might feel nudged towards string-related work, even if they are personally skeptical, simply because that is where many of the positions and grants have historically been. In that sense, the growth of string theory may reflect not only its scientific merits, but also the human dynamics of scientific communities. Perhaps the most serious concern, though, is about falsifiability. If string theory, with its immense landscape and multiverse possibilities, can accommodate almost any set of observed constants by pointing to some region of the landscape where those values occur, then it risks becoming impossible to rule out. A theory that cannot, even in principle, be proven wrong by any observation begins to drift away from what we usually mean by a scientific theory. String theorists have responses. They point out that many of the great theories in physics began as mathematical frameworks that only gradually grew predictive power. Quantum mechanics itself started as a mathematical apparatus that took time to connect fully with experiment. They argue that the internal consistency requirements of string theory are extremely restrictive, carving out a small island in the ocean of imaginable theories, even if it is still hard to convert those restrictions into clear experimental tests. They also emphasize the surprising side benefits of the theory. Work inspired by string ideas has led to advances in pure mathematics and has suggested new tools for studying strongly interacting quantum systems, from exotic materials to fluid dynamics. Even if string theory does not turn out to be the final theory of everything, they say it has already contributed valuable concepts and methods. In the background of this debate lies a softer, deeper question. How does science move forward when direct experiments are difficult or impossible? How long should a promising but unconfirmed idea be pursued? At what point do elegance and internal logic stop being enough? There are no simple answers. The conversation continues, sometimes heated, sometimes gentle, as physicists balance their desire for clarity against the allure of a beautiful idea. As you rest in the quiet space between waking and sleep, you can let this tension drift through your thoughts. On one side is the human love of order, symmetry, and graceful equations. On the other, the stubborn, messy reality that only reveals itself through observation. Perhaps the ultimate measure of string theory will not be whether it is pretty, but whether it truly helps us hear more of the cosmic music, to understand how our small lives fit into whatever the universe really is. And then there is the practical, almost childlike question. How could we ever hope to prove that tiny strings exist if they are far smaller than anything we can measure? Testing string theory directly is like wanting to examine the fine brushstrokes of a painting that hangs on the other side of the solar system, armed only with a magnifying glass. The characteristic length of strings is thought to be near the Planck scale, a realm of distance and energy so remote from everyday experience that it defies intuition. If you could enlarge an atom until it filled the entire solar system, a string inside it would still be far thinner than a human hair. To probe physics at that scale directly, we would need particle collisions with energies perhaps 1,000,000,000,000 times higher than those produced in our most powerful accelerators today. Building such a machine would require an apparatus larger than our galaxy, a project so far beyond our reach. that it might as well belong in myth. This does not mean string theory is completely beyond testing, but it does mean the tests must be indirect and subtle. Instead of trying to see strings, physicists look for gentle fingerprints that stringy physics might leave in phenomena we can observe. Supersymmetry is one such fingerprint. If superpartners exist and are not too heavy, they might be created in high-energy collisions and leave recognizable patterns in detector data. The Large Hadron Collider near Geneva has spent years searching for these signals. So far, no unmistakable signs of selectrons, photinos, or other superpartners have appeared. That absence pushes the possible masses of these particles higher, but does not rule them out entirely. They may simply lie beyond the energy frontier we have reached so far. Another route is to look for evidence of extra dimensions in how gravity behaves on very small scales. If gravity can leak into hidden dimensions, it might become slightly stronger than expected at tiny distances. Careful experiments measuring the gravitational attraction between very small objects at short separations try to detect such deviations from the predictions of Einstein's theory. So far, gravity has been stubbornly conventional, but the measurements continue to improve. Physicists also search for hints of extra dimensions in high-energy collisions. If some of the energy in a collision disappears into hidden directions of space, it would show up as missing energy in our detectors. A few puzzling events have been seen over the years, but none have yet provided clear, repeatable evidence of extra dimensions. Black holes offer another potential window. If string theory's description of black hole entropy and information is correct, it may make specific predictions about the spectrum and behavior of the radiation black holes emit as they slowly evaporate. Unfortunately, the black holes we can observe in space are enormous. They radiate at temperatures so low that their quantum glow is utterly drowned out by other astrophysical processes, and they would take far longer than the current age of the universe to evaporate appreciably. Because of this, some researchers have turned to analog systems, carefully designed laboratory setups that mimic certain aspects of black hole physics. In these experiments, sound waves in flowing fluids or light moving through specially crafted materials can behave mathematically very much like waves near a black hole horizon. By studying how these analog systems emit radiation and store information, physicists hope to catch at least a faint echo of the same principles that might govern real black holes in a string-theoretic universe. Those tabletop black holes, made from sound waves or light, cannot reach the true depths of quantum gravity, but they still matter. They let physicists test some of the same quantum principles that underlie string theory's approach to real black holes: how horizons behave, how information might be encoded, how radiation can emerge from boundaries. They are like gentle sketches of a painting we cannot yet see up close, hints of a deeper picture waiting far beyond our current reach. On a much grander scale, cosmology may be the richest playground for stringy ideas. The extra dimensions, vibrating strings, and intricate ways of curling space that appear in string theory could have left faint fingerprints on the earliest light in the universe, the cosmic microwave background, the afterglow of the Big Bang. We can measure this ancient light with exquisite precision, mapping tiny temperature ripples across the sky. Some versions of string theory suggest that these ripples should have particular patterns, subtle correlations, small deviations from perfect randomness that reflect how fields behaved in the very early universe, when stringy physics mattered most. Future observations, with sharper instruments and deeper surveys, might be sensitive enough to pick out these delicate signatures, like hearing a quiet violin line beneath the louder instruments in an orchestra. String theory also predicts the possibility of cosmic strings, which are not the fundamental microscopic strings of the theory, but large, extended objects that could have formed as the universe cooled and different phases of fields emerged. If they exist, these cosmic strings could stretch across vast distances in space. Their gravity would bend the paths of light from galaxies behind them, creating distinctive patterns, double images, sharp line-like distortions in the large-scale maps of the sky. Astronomers have searched for such signs. So far, none have been confirmed, but the sky is vast, and the searches continue. Closer to home, some of the mathematics born from string theory has found a role in understanding exotic materials, certain phases of matter, especially those where particles are strongly entangled and do not behave like simple collections of individual bits, can be described using tools that resemble those of string theory and holography. Vortices in superfluids, excitations in unusual conductors, and other collective phenomena sometimes behave like effective strings in a condensed matter setting. These systems do not test fundamental string theory directly, but they show that string-like physics can emerge naturally from complex interactions. Perhaps most intriguingly, string theory and the holographic principle have deep connections to quantum entanglement and information theory. The idea that geometry and information are intertwined, that the shape of space-time might encode the pattern of quantum correlations, is now being explored in controlled laboratory systems. Small arrays of atoms, photons, or superconducting circuits can be entangled in precise ways, and their behavior compared against holographic predictions. These experiments do not prove that our entire universe is holographic, but they do test some of the same mathematical relationships between entanglement, geometry, and information that string theory suggests should be fundamental. The difficulty of testing string theory has pushed physicists to invent new kinds of calculations and new ways to think about geometry. Techniques for dealing with very complicated quantum systems, methods for analyzing extra-dimensional shapes, and tools for extracting predictions from dense webs of equations have all grown out of this effort. Even if strings themselves turn out not to be the final answer, these methods have already spread into many corners of physics and mathematics, helping us understand everything from fluid turbulence to number theory a little better. Some scientists suggest that string theory might be best viewed not as a single, sharply testable theory, but as a broad mathematical framework, a language that can organize and unify many different physical ideas. Seen this way, its value lies in the connections it reveals, the dualities it uncovers, and the techniques it inspires, even if its direct contact with experiment remains elusive. Others push back, insisting that physics must remain an empirical science at heart. However beautiful the equations, they argue, a theory must eventually meet observation if it is to be considered a description of the world and not just an elaborate mental construction. And so the search goes on, late at night, in quiet offices and softly humming labs. Scientists sift through data from particle collisions, from telescopes, from precision measurements of gravity and quantum systems. They look for small deviations, unexpected patterns, little whispers in the noise that might hint that the universe really is built from vibrating strings, really does shimmer with extra dimensions, really does encode itself holographically. As you drift toward sleep, you can picture them there, bathed in the glow of screens and equations, following faint trails through a forest of data in the hope of catching even the softest echo of a string. Sometimes, in physics, the equations come first. They arrive with a kind of quiet inevitability, beautiful in a way that is hard to explain but impossible to miss. Long before we fully understand what they mean, we sense that they are telling us something important. There is something mysteriously compelling about mathematical beauty, a feeling of rightness when a collection of symbols fits together with unexpected grace. Physicists often speak of elegant equations, of symmetries that feel natural, of theories that seem too harmonious to be mere coincidence. String theory is one of the purest examples of this pull. Its mathematics is rich and intricate, woven from geometry, algebra, and topology in ways that have surprised even the people who study it. Many of those who work on string theory are drawn as much by its beauty as by the promise that it might explain the universe. But what does it really mean for mathematics to be beautiful? Sometimes beauty shows up as simplicity, as a deep idea captured in a single short expression. Einstein's relation between energy and mass E equals mc squared is one example. In just a few symbols, it reveals that matter and energy are different faces of the same thing. That compact equation reshaped our understanding of stars, nuclear reactions, and the very structure of space-time. String theory's beauty is of another sort, the beauty of unification and internal consistency. It does not focus on a single phenomenon in isolation. Instead, it tries to weave particles, forces, and space-time geometry into one coherent tapestry where each thread supports the others. In its most ambitious form, no part of the theory stands alone. Everything is connected through symmetries and dualities. It is like a vast musical composition in which motifs repeat, transform, and echo across movements, so that a theme introduced in one instrument returns later in another, changed, but recognizably the same. The mathematics that appears in string theory often seems to have a life beyond physics. Calabi-Yau manifolds, those six-dimensional shapes that may describe the hidden dimensions of space, were studied purely for their mathematical interest, long before they were linked to physics. When string theorists realized that different Calabi-Yau shapes could be related through something called mirror symmetry, they uncovered deep connections between geometric spaces that mathematicians had never suspected. This discovery, born from physical considerations, led to new theorems and insights in pure mathematics. The holographic principle is another example of this strange two-way street. The realization that a theory in a higher dimensional space with gravity can be equivalent to a theory on a lower dimensional boundary without gravity is not just a clever trick. It is a profound duality, a dictionary that translates between two seemingly different languages. Problems that are hard in one picture become simple in the other. Hidden structures emerge when you look at the same physics from a new vantage point. These dualities may be string theory's most alluring feature. They tell us that what appears to be one kind of world from one angle can look like a completely different world from another, and yet both descriptions are equally correct. It is as if the same piece of music could be heard as a gentle waltz by one listener and as a fiery tango by another, each rhythm emphasizing different accents, yet both perfectly faithful to the same underlying score. Still, the relationship between mathematical beauty and physical truth is delicate. History contains many examples of theories that were mathematically lovely, but ultimately did not describe nature. There are also theories, like the Standard Model of particle physics, that work astonishingly well, but look messy, full of seemingly arbitrary parameters and irregular patterns that offend some aesthetic tastes. This raises a quiet but serious question. Is mathematical beauty a reliable guide to the structure of reality, or is it simply a reflection of how human brains like to organize patterns? Some physicists argue that the universe has no obligation to satisfy our sense of elegance. Nature might be fundamentally complicated, and our preference for simple, symmetric laws may be more about comfort than truth. Others point to the uncanny way mathematics has predicted phenomena long before they were observed. Quantum mechanics and general relativity were guided by aesthetic and conceptual considerations well before their full experimental confirmation. The phrase, "the unreasonable effectiveness of mathematics," captures this puzzle. Somehow, structures invented in pure thought often turn out to describe the physical world with astonishing accuracy. String theory sits at the extreme edge of this debate. It is so mathematically complex, and its experimental foothold so limited, that much of its support rests on beauty, consistency, and the richness of the structures it reveals. If the theory turns out to be right, it will be a striking victory for the idea that mathematical elegance is a trustworthy compass. If it turns out to be wrong, it may teach us that beauty alone is not enough, that our aesthetic sense, powerful though it is, must be checked again and again against the stubborn facts of observation. There is also the question of whether beauty is something objective in the fabric of the universe or something subjective in the architecture of our minds. Perhaps we find certain patterns beautiful because our brains evolved to notice the regularities that actually occur in nature. Or perhaps our notion of elegance is shaped by culture, training, and habit, and does not necessarily track the true structure of reality. What is clear is that the beauty of string theory has shaped the path of physics for decades. It has drawn many bright minds into its orbit, driven the development of sophisticated mathematics, and inspired new ways of thinking about space, time, and information. At the same time, it has raised concerns that our field may sometimes chase elegance at the expense of connection to experiment. As you rest in the soft borderland between waking and dreams, you can hold this mystery lightly, the way equations can feel right long before we know if they are. Whether or not string theory ultimately describes the world, it has revealed hidden harmonies in mathematics and suggested that the universe, at some level, might be organized with a depth and subtlety that our minds find beautiful almost by instinct. Those structures may live only in our imagination, or they may mirror the very architecture of reality itself, a score written in a language of numbers and shapes, waiting for us to learn a little more of the tune. In the soft space between waking and sleeping, between equations and starlight, between what feels beautiful and what we can prove, a quiet question lingers. Is the universe really made of music? And if it is, are we slowly learning to hear its song? If string theory is right, reality is stranger and more lyrical than our ancestors ever dared to imagine. After wandering through hidden dimensions and vast galaxies, after picturing vibrating strings, holographic horizons, supersymmetric shadows, and branching multiverses, we arrive at a gentler question beneath all the technical ones. What would it actually mean to live in such a universe? What would it say about who you are, where you belong, and what it means simply to exist? In the string picture, the most basic fact about reality would be that everything is vibration. Every particle, Every force, every invisible field, every drop of matter and flicker of energy would be different ways the same fundamental strings can sing. The electrons in your atoms, the photons carrying the light that reaches your eyes, the gravitational field that keeps you nestled on your bed, all of them would be notes in one cosmic composition. That would mean the wild diversity of the physical world. All the different particles and forces that look so separate is like a trick of perspective. At the deepest level, everything is the same kind of object, moved into different patterns. The universe would be more like a single instrument than a crowded orchestra pit. One underlying string device, capable of producing piccolos and drums, choirs and bells, simply by changing the style of vibration. The implications of this unity are quietly profound. It would mean you are literally connected to everything else in existence at the most basic level possible. The strings humming inside your thoughts would be the same kinds of strings that shape distant stars, black holes, and swirling galaxies. When you gaze up at the night sky, you would not be looking at something foreign. You would be looking at distant phrases of the same underlying music that makes you possible. String theory also whispers that space and time themselves, the stage on which everything seems to happen, might not be the deepest layer. They could be like the smooth surface of a lake, emerging from the coordinated motion of countless water molecules. In the same way, the space-time you move through could arise from the collective behavior of vibrating strings in a higher dimensional realm. If that is so, then the categories you use to organize your life before and after, here and there, cause and effect, might be very good approximations for everyday scales, but not truly fundamental. At the string scale, the neat lines between space and time, matter and energy, even self and other might blur into a single, more unified structure. The universe would not be a set of separate things in a container, but patterns within a deeper, continuous process. The holographic principle pushes this interconnectedness further still. If reality is holographic, then every region of space would, in some encoded way, contain information about every other region, the way each piece of a hologram can reconstruct the whole image. In that picture, you would, in a very abstract sense, carry information about the entire universe, and the universe would carry information about you. The boundary between in here and out there, between observer and observed, would be less like a wall and more like a convenient line we draw for ourselves. The extra dimensions of string theory expand this feeling of richness. If there really are hidden directions folded into every point in space, then your everyday three-dimensional path is only part of the story. You would be moving through those extra dimensions constantly, even while you sit still, like an ant walking on a beautifully carved sculpture, aware only of the thin path beneath its feet and not the intricate relief rising all around it. The multiverse idea stretches the imagination even more. If string theory's landscape is real, then the universe, you know, might be just one bubble among many in a vast foam of realities. Each bubble could have different laws of physics, different particles, different patterns of space and time. In that wider view, every way the equations can consistently sing might be realized somewhere. Every path not taken here might unfold in some other branch of existence. From where you sit, you would remain bound to your own branch, unable to visit the neighboring universes, much like a fish held within its own stream. Yet you can still let your thoughts wander over the idea of an endless garden of possible worlds, all blooming in the dark with their own versions of stars and stories, or with no stars and no stories at all. String theory's ties to information hint at something about mind and experience as well. If the holographic principle is truly fundamental, then what you perceive as physical reality might best be thought of as information being processed in a particular way. The unfolding of the universe would be a kind of cosmic computation where the flow of information is not a description of reality, but reality itself. In that light, consciousness could be seen as a special mode of this information flow, the universe briefly forming patterns that can notice, remember, and reflect. Your awareness, your sense of I am, might be the cosmos, examining a tiny part of its own code from the inside. You would not be something separate added onto the universe. You would be one of the ways the universe experiences itself. The mathematical elegance of string theory adds another quiet layer to this picture. The fact that structures invented by human minds to solve abstract puzzles seem to resonate with the deep architecture of the world suggests either that we have been shaped to understand certain kinds of patterns or that reality itself has a mathematical backbone. If string theory's equations truly match the universe, then mathematics would not simply be a language that we impose on nature. It would be a discovery of relationships already woven into the fabric of existence. The symbols on the page would be glimpses of the universe's own internal logic. All of this points toward a view of existence that is more miraculous and mysterious than daily life usually reveals. If reality arises from vibrating strings in higher dimensions, if space-time is emergent, if information and consciousness and geometry are all aspects of the same underlying process, then being alive is less like sitting in a room inside a universe and more like being a swirling pattern within the universe's own music. You would not be a separate object traveling through a backdrop. You would be a temporary theme in an endless composition, a melody that begins, unfolds, and eventually fades, but is never truly disconnected from the score that gave it shape. Your thoughts, memories, friendships, worries, and hopes would be real and important, but also expressions of something larger and deeply interconnected. String theory does not answer the oldest questions, why there is something rather than nothing, or why the laws are what they are. But it does suggest that whatever the answer is, it is likely to be stranger, more unified, and more beautiful than we once imagined. If the theory is roughly right, then you are not just in the universe, you are the universe, looking back at itself through a narrow, tender window of experience. The cosmic symphony is not happening somewhere far away. It is happening as you breathe, as your heart beats, as your thoughts drift and soften. And so, in this quiet moment, you can simply rest with the possibility that everything might be music. The smallest vibrations could underlie the largest structures. Hidden dimensions might be curled into every point of space. The forces that hold stars together and the particles that build your cells might all be moving to the same silent rhythm. You have wandered in thought through supersymmetric shadows, holographic horizons, and infinite landscapes of possible worlds, and circled back to something gently simple, a sense of deep connection. If reality is a song, then you are one of its phrases, unique and fleeting, yet made of the same notes as everything else. As your own inner vibrations slow and settle into the rhythm of rest, you can let that feeling of connection stay with you. Whether or not the universe is truly built from strings, the search to understand it has revealed possibilities more delicate and wondrous than any single lifetime can hold. Somewhere between mathematics and moonlight, between the known and the unknown, the universe continues to play whatever song it is playing. Tonight, you are part of that song, Let it cradle you. Let it carry you. And if your dreams wander among stars and hidden dimensions, they will still be made of the same quiet music that hums beneath everything.